last day. So it's a pleasure to share this session, and so we will pass the to Charo, and I hope you will enjoy this third day of the workshop, and as in the previous days. So please stop when you think it's proper. Where you is certainly will help with answers to your questions. So Charo.
Thank you. And yes, I will just say the same thing. Please stop whenever you want. If you have questions, as usual, just ask right away. So, so we have seen a lot of stuff with higher order networks. We discussed various types of applications, various situations, and whatnot. So, what I would like to start today to talk about is, suppose you want to do some calculations with higher order networks. So typically, if the higher order network is really, really small, like 8 nodes or something like this, you can do it by hand. If you're trying to do some proper theoretical thing, you can do it by hand. But often you want to try to simulate these in a computer. You want to make a model, and you want to do 1 million nodes or something like this, and you want to run a simulation. So how do you do that? You say, okay, fine, I sit myself there on the keyboard and I write the code and I run the simulation. And in principle, that works. The problem is that you need to be a bit careful when you do this. And you need to be a bit careful because when you have a traditional network, as we started this whole thing, like we started saying in a traditional network, you have the adjacency matrix. And the adjacency matrix encodes the entirety of the structural information of your network. If you want, you can store the matrix in a computer. That is usually not the best thing you can do, but if you want, you can do that. Alternatively, you can store just the edges and stuff like this. But when you are with higher order networks, if you try to, store the whole of the information, so if you try to store all the adjacency tensors for all the orders of interactions that you have, you end up very quickly into serious trouble. Just to fix the ideas, imagine that you are just using a k-uniform hypergraph. So all the edges have the same size. And just say you take in size 3 or size 4, okay? Even just with size 4, if you use a naive data structure, so a naive way in which you are storing the data in the computer, you're going to run out of memory in like no time at all. As soon as your network is more than, I don't know, maybe 15 nodes, you're out of memory. The reason kind of like it's easy to understand. If you have a matrix is a grid of numbers, a two-dimensional grid of numbers. Okay? If you have a 3-uniform hypergraph, then it's like a cube of numbers. If you have a 4-uniform hypergraph, you have a 4-dimensional thing. So the amount of numbers, the amount of memory you need to allocate, which starts growing like instead of n squared, starts growing like n cubed, and to the 4th, and so on and so forth. So if you do it naively, you cannot do it. You just run out of memory very, very quickly. So, okay. So what is the goal here? The first goal is to see how we can define, how we can create a data structure that minimizes the memory footprint of the data, meaning that it uses as little memory as possible, and then, of course, trying at the same time to build the algorithms of this data structure in a way that is as efficient as possible. This is a drawback, okay? This is not drawback, sorry. It's a balance here. It's a balance that we need to strike. A trade-off, yeah, a good one. A trade-off that we're trying to do. If you make the naivest possible data structure, then obviously you can immediately just go and check, is the link there, yes, no. You can quickly do your matrix multiplications if that's what you need to do all sorts of operations. If you make a data structure that is extremely compact, you may end up having to do much more complex algorithms to read and write. So we're going to strike a balance within this trade-off. That's the first goal of today. So in order to do so, we need to exploit some pieces of information that we know. Because obviously, if you don't have any information, then you don't know what to do. If you already know something about it, you are decreasing the information entropy of your problem, and therefore you need to spend less effort in order to solve it. So the first thing that we're going to use is the fact that in most cases the hypergraphs that we deal with in higher order networks are simple, which means what we said the first day, that you have no repeated edges and no repeated nodes within each edge. That is good. This is good because the adjacency tensors that we're dealing with are hypersymmetric. What does it mean that they are hypersymmetric? It means that you're guaranteed that all the elements on all the diagonals, not just the main diagonal, the hyperdiagonal, are necessarily zero. This is going to be an important point later on. Number two, real-world data usually is sparse. So we're going to do something that will work well with sparse data, but that does not assume sparse data. Meaning, if the data are sparse, yay, good, it's going to be fairly efficient. If the data are not sparse, okay, tough luck, but it's still going to work, it's still going to be as efficient as possible. Now, the first thing that this leads to, these two things I just said, is that we don't need to store every element of the tensor. We don't need to store every element of the tensor because some elements are necessarily zero, many elements are going to be zero because of sparsity, so we're going to have to find a way that we can only store some parts of the data and at the same time still be able to do what we want to do, that at the end is kind of like linear algebra on steroids. So, I'm slowly giving you like one consideration to the next, to the next, to the next, to build up the idea and then actually do it. So what we're going to do is we're going to do this. The drawing that you can see here, hey, what is this? I'm going to explain what it is. We are not going to store everything, okay? We start by exploiting the symmetry of the tensor. If the tensor is symmetric, we only need to care about the uppermost hyperpyramid in the equivalent geometric structure of the tensor. So if you have a 3 uniform hypergraph, where that's basically a cube, as I said, then this red region is the uppermost hyperpyramid, and we only care about there. Anything else in this cube, you don't care, because all the information will simply be repeated and will be contained already inside that. So that's the first, the first idea. Well, number two, all the elements on the hyperdiagonals, all of them are going to be zero, which at this point already leads us to what we want to do in a sense of shape of what we want to do, because at this point what we can just do is write down our data like this. Actually, for the moment, let me write it this way, sorry. We make a vector, and this vector is a vector of rows. Now you see, a vector of rows is basically a matrix. Kind of, okay, this is not going to be a matrix, this is going to be a matroid at the end. But for the moment, just let's look at it like this. So, like here, okay? So, each of these rows over there will be one part of that cube, of this cube over here. Okay? Each of these rows there. Precisely, each row will be the line in that cube that corresponds to the first k-1 indices of the tensor that are fixed. And you're just scanning the last one. Okay? And then we have all the other ones, and each element, each index corresponding to the elements of a single row will be the last index in the elements of the tensor that we are dealing with. Effectively, what I'm saying is that we're doing this. We are scanning the tensor like this. This is again the example for size 3, but it works exactly the same in any size. It doesn't matter. So we are scanning here the tensor with a straight line in some direction. Doesn't matter which direction it is, so long as you always do it in that direction. And then we make this blue line here move in the remaining k-1 directions. So here, if it's 3, and we're choosing this direction as the direction of the line, we're going to make this line move in the other 2. So kind of like scan here, scan the next, scan the next, scan the next, scan the next, next down, scan, 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 next down, scan, scan, scan. Kind of like a tomography, kind of like a tomographic scanning of the tensor. So this is how we're going to do. You can also start noticing here something, which I hope I will say it explicitly in a few seconds, but keep in mind that figure. So the thing there, actually, you know what, is this. The thing here is that I said before we only care about the red part, right? But the raw scans the entirety of the span of the tensor. But now notice it only intersects the red part here. So this means that each of these rows, this blue row here is like this row here that I drew on the board, each of these rows over there doesn't need really to be stored in its entirety because we only care about this part here. So we only need to care about the intersection of these rows with the uppermost hyperpyramid of the tensor. Also, if the data are sparse, chances are these intersections are all zeros. There's no edges there. So this means even less stuff to have to record. We concluding, in a sense, this initial kind of like reasoning, what we want to do is we want to store only the rows here that have something in it. And of the rows that do have something in it, we only store the intersection region here between the row and the uppermost hyperpyramid of the tensor. So this way we are reducing more and more and more the amount of stuff that we need to actually store. Again, if we have any elements that are necessarily zero for some reason or another, or because they don't exist, we can simply avoid storing them, which is another point here. If the data are sparse, many of them are zero, so we don't care about the zero. We completely avoid even storing them, which means we only store the elements that are one. Now, since the hypergraph is simple, and the elements are either 0 or 1, it means we actually don't even store the elements that are 1. We only store the locations of the elements that are 1. And as we're going to see later on, this can be done fairly efficiently if you use a programming language where you can address directly and especially unsafely the memory of the computer itself. So if you try to do it in Rust, if anyone likes programming or programming languages, if you try to do it in Rust, Rust tells you no fucking way, because it's kind of like a safe programming language that tries to avoid doing like stuff with memory that is unsafe. If you do it in C, it's perfect because C allows to shoot yourself in the foot if you want. In fact, most of the bugs that happen are exactly bugs of this kind, but then again, the trade-off is that you can do more efficient things. So let's see, we've done this, we've done this, we've done that. Oh yes, the last thing to say is that many of the rows there will very likely be zero, will be zero anyway. So regardless if there are data or not, many of the rows will necessarily, I shouldn't say they will be zero, will necessarily be irrelevant. That's more precise. The reason is this. Suppose, okay, before I chose the other direction, I said the direction is irrelevant. Here I just drew it this way to make the point clearer, but it doesn't really matter. It's, it's the same in any direction. If you look at this row over here, this row does not intersect the uppermost hyperpyramid. So this row here, if we were scanning in the vertical direction here, this row here, we don't even care about it, wouldn't need to care about it because it's not, cannot intersect the uppermost hyperpyramid. Now, since these rows always have a same dimension, dimension is one dimension, but the tensor may increase for this k equals 3. If you go k equals 4, k equals 5, etc., etc., the higher the dimension, the higher the saving of memory that you do by realizing that you don't need to store, don't even need to care basically about these rows. Okay? So with this is like the last considerations, we can say, fine, what we want to do, what we want to build as a data structure will look like this. So what we need in our structure is, number one, we need a counter, which is just a number. The number tells us how many rows we have actually stored. Reason is, as I said, some rows will be empty, some rows will necessarily have zero intersection, some rows will be zero for other reasons, some will be zero because there is no data, etc., etc. So in many cases, we are not going to store them all, which means we need to know which ones we are storing and how many they are. So first element is a counter that tells us how many rows we are storing in our structure. Number two, we need to know which row is which. Like, which row is this one, which row is this other one, which means we need a set of identifiers. Kind of like, this is row number 1, this is row number 20, this is row number 30. What these identifiers will be, we're going to see it in a short while. But obviously, we need to know what is what. So number two thing we need is an ordered list of numerical identifiers of the rows. Number three, we need to know how many elements are in each row of those that we have stored. This is why, I said before, a vector of rows is a matrix. I said, but this is not a matrix, this is a matroid, because each row doesn't necessarily have the same length. So rather than being something like this will be more something like this. Some rows will be longer, some rows will be shorter, and we need to know how long each row actually is. Number three. Number four, the data. So this is this is metadata. The first three are metadata. It's data about data. The last one over here is the actual data. So the actual data that we're trying to store. Okay. Finally, for reasons that are more related to the algorithmic part of this data structure, we need three extra auxiliary quantities. One of them here is a vector of length n. We will see why. And two of them are two vectors of length k, where k is the dimension of the tensor. By the way, if you have a general hypergraph, not a k-uniform hypergraph, obviously you will just store one of this structure for each of the constituent uniform sub-hypergraphs. So you basically do all the edges of size 2, all the edges of size 3, all the edges of size 4, and you have all the structures like this together. And of these two vectors, by the way, one of them is, well, in my idea here, just use it to store the indices of the element that you want to address. So this is how it's going to look like. If you program in C, this is how you would define it, basically. Just define a type as a structure, you call it symmetric tensor or whatever you want, and you need these elements like this. There's some other considerations we're going to do about it, but basically this is how it's going to look like. And can I click? Click. There you go. So once this is set, we need four things here, four main algorithms. Okay. One is something that creates a tensor in its initial structure. For those that like object-oriented programming, sometimes these are called constructors. So you need to define a constructor. Then you need to define something that will destroy this structure, so a destructor, something to clear it away. And then you need something to read and something to write. That's pretty much it. So we need four things. So the constructor to initialize the structure is kind of like fairly simple, because all you have to do is number of rows. Remember, initially the number of rows is 0 because you just created something. You haven't yet recorded anything into it. So when you just start, the initializer needs to make the initial number of rows that are 0. All the various vectors, this one's over here, the list of the numerical identifiers, the list of the lengths of each rows will just be empty. So you just say, okay, it's going to be something over there. The actual matroid, again, so the data is going to be empty. So you just create everything there. They're just there. If you do it in C, you just allocate some memory for these vectors and for the structures, and you don't do anything else. So that's like fairly simple. The destructor is kind of equally simple, because all you have to do is you just free the memory for the vectorial quantities and for simply the the thing, the counter, that you don't even need to do anything, because at the end it's going to be an integer, most likely, in most cases, a short integer, so who cares? So basically, what we need to actually see how to do it is how to read and write. That's a little bit more complex. However, before that, what we need to know is how to know what row each row is. Because, as I said before, we are not going to store everything inside here. We're only going to store some of the rows. So how do you know which row is which? Now, we do this the following way. Suppose, if for a reason or another, we want to do it the naive way. So the naive way will be we store absolutely everything. So every row in that representation, we store it. Okay, fine. But then, if we did that, right, then we would have chalk. I'll do it. If we did that, then we would have the first row that will correspond to the first k minus 1 indices that are fixed, and especially the first k minus 1 indices that are all 0. So this is like 0, sorry, I have a mosquito here, 0, 0, dot, 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 0, and then here you have 0, 1, 2, 3, 4, etc., etc. The second row will correspond to the first, and these are, excuse me, k minus 1 indices. The second row will be like 0, 0, 1, and again 0, 1, 2, 3, 4, and so on and so forth. Right? So then later, you will have here 0, 0, dot, 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 n minus 1. And again 0, 1, 2, 3, 4. And then you go 0, 0, dot, 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 1, 0. So each row in sequence would correspond to a sequence. Mosquito loves me. It will correspond to a sequence of the first k minus 1 indices that is exactly like this. Okay? This will be the first row, this will be the second row, and so on and so on and so on. Okay, so no one tells us that we cannot still use these as the identifiers of which row is which, even if, for example, we were to just store only this one and then the next one is this one. Say this is this and then this one will be this. We can still use these indices here as the recipe to give us the numerical identifier of the row that we are storing. But if you look at this, right, and if you count row number 1, row number 2, row number 3, row number 4, these here are just the digits of a number in base n. It's like, you know, when you count in base 10, we count in base 10, but you may count here in base n. And these are the digits of the number in base n. So the numerical identifier of our row is simply the representation in base, the representation in base 10 of these numbers here, whose indices, whose digits in base n are given by the first k minus 1 indices of the elements of the tensor that will correspond to that row. Okay? And the formula is that this is nothing. This is nothing like magic. This is simply what I just said, but written like that. It's like saying, you know, if you take a number, if you take number 1, 2, 3, 4, it's like 4 units, 3 tens, 2 hundreds, 1 thousandth. Here, instead of having the powers of 10, we have the powers of n. That's it. And you take the first k minus 1 indices of the tensor. Here in this formula here, I use I as being the indices of the tensor for the elements that we are considering. So this gives us the formula for the row identifiers. So now we know how to address those things, which means we need to figure out how to read and how to write. So Stefan is gone. Stefan just mentioned us before that at a certain point in in an episode that planted the seeds for the birth of Renaissance in Florence, intellectual people were considered those who knew how to read and write. So we are planting here the seeds for the Renaissance of higher order networks, and we need to know how to read and write. This this thing here, the previous one, in a kind of like perhaps outdated style in a flowchart, I don't know if they're still used today, is how the algorithm for reading is going to be. And this is probably way too small to read, obviously, but we're going to zoom in and examine each step, each part of the flowchart step by step. So the beginning, the first thing that you need to do is what I call an existence check. This is literally the first part of the flowchart. I'm literally like zooming here and then zooming down. That's what we're going to do. Okay. So the first thing we are reading here, the first thing you have to do is to check, does the tensor even exist? Is the tensor empty? Yes or no? So how do we do that? Remember the number, how many rows were stored? The counter, if that counter is 0, then obviously the tensor is empty because there's nothing that has been stored, so it's empty. If that is the case, then it's over. You don't have to do anything, just return 0, because whatever element you're trying to read is obviously 0 because the entire tensor is empty. Good? Then suppose instead that the tensor is not empty. If the tensor is not empty, well, we need to do something else. We do a pigeonhole count of the indices of the elements that we are dealing with. So, do you know what a pigeonhole count is? No, no, yes, no, no, no. I see one yes and everybody no. Okay, good. So pigeonhole counting is the idea that is behind the pigeonhole principle, which incidentally is also the idea that is behind the existence or lack thereof, theorems of existence or lack thereof, of injective functions between different types of domain and codomain. It comes from there, and in its classic original discrete form is the following thing. Suppose you have a bunch of numbers. Okay, suppose you have a bunch of numbers and you want to sort them. How can you do that? If you know the range of these numbers, I'm not saying this is efficient, I'm just giving you the idea here, okay? If you know the range of the numbers, say the numbers can go from 1 to 100, what you can do is you can create a nice bunch of pigeonholes, little squares made of wood, numbered from 1 to 100. And then you take your numbers written here, and you read them and say, I find 3, and I put a little stone in the 3. And next is 4, I put a stone in 4. And next 3 again, I put another stone in 3, and so on and so forth. Okay? At the end, if you read the sequence in sequence, you know precisely you have it sorted, and at the same time you know how many times you had number 1, and that's the number of stones you have in box 1, how many times you had number 2, how many times you had number 3, and so on and so forth. So the first thing we do, if the tensor is not empty and we're trying to read an element, is exactly this, a pigeonhole count. That. Now, why we do the pigeonhole count? Because what we want to do is we want to exploit symmetries and check for symmetries. So you see, this is like an idea. We have 5, 1, 5, something else, 3. So I see a 5 and I put a 1 over here. Then 1, I put a 1 over here. Another 5, so I'm increasing this. It was 1, now it's 2. And so on, and then 3, like this. So this is where we use the auxiliary vector of size n, okay, to do exactly this. So why are we doing this? Well, we're doing this because after doing it, we can now read this vector from the start to the end. And what we can do is we can check whether any of the numbers in this vector are greater than 1. So here, 1, here is nothing means 0. So 1, 0, 1, 0, 2. Aha, now 2. 2 is greater than 1. But if 2 is greater than 1, then it means that this thing here, which is 1, 2, 3, 4, 5, box number 5 is greater than 1, means that index number 5 appears more than once, in this case 2, in the list of the indices of the element that we're trying to read. Okay, but if that is the case, then that element lies on one of the hyperdiagonals of the tensor. but the tensor is hypersymmetric, which means that that element is necessarily 0 because it's on one of the hyperdiagonals. So if that is the case, click. Click. So if that is the case, the element is 0, and you can just directly return 0. That's it. You know that it's on the hyperdiagonal. You don't have to do anything. It's just 0, guaranteed. Alternatively, the element is not on a hyperdiagonal, which means we need to do something else. If that is the case, then the next thing to do is we take and we sort the indices. Why do we sort indices? And incidentally, this is where we use another of the auxiliary vectors of size k. We sort the indices because now we want to exploit again symmetry, but in a different fashion. Remember, we are only storing the uppermost hyperpyramid, so we don't need to care if the element is somewhere else, because everything will be always mapped to the uppermost hyperpyramid. So everything will always be mapped so that the sequence of the indices of the element of the tensor is either strictly increasing or strictly decreasing. We know it has to be strictly, because if it's non-strictly increasing or non-strictly decreasing, it means that at least two of the elements are the same, which means again that you are on a hyperdiagonal, which means automatically you know that it's 0. So, by the way, it doesn't matter if it's strictly increasing or strictly decreasing, because if you're storing the uppermost or the lowermost hyperpyramid, or if in your mind the uppermost hyperpyramid corresponds to strictly increasing or strictly, it doesn't matter, so long as you stick with your convention, okay? In fact, I don't even remember when I implemented this which convention I used. It doesn't really matter, as I said. So this is why we sort the indices. Then after sorting the indices, this is what I just told you. After sorting the indices, we go and we find the number here. How do we find the number of the row? By taking the first k minus 1 indices and plugging them in the previous formula, the one that I showed you before, the one here with the numbers in base 10, numbers in base n. So that tells us the number. Is a question? Okay, that tells us the number of the row that we're trying to address. Yes? Okay, one moment, you say? Microphone to the student, please.
Hello? Yeah. Sorry, I want to ask you, I didn't understand what you said. This thing that if the indices are repeated, you can return 0, like you know that they are in the hyperdiagonal.
Moment. I can draw it better. Moment. Two-dimensional, okay? Okay? The elements on the diagonal are those where the indices are repeated. Wait. Three dimensions. Here, let's say this is again 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3. 0, 1, 0, 0, 1, 1, 0, 1, 2, 0, 1, 3, etc., etc. On this face over here, only the last two elements will be repeated, and you are on this diagonal. Over here, instead, so here, which one have we done? 0, so this is going to be, so this number is again 0, 0, 3 over here. So this one is going to be 0, 1, 3, 0, 2, 3, 0, 3, 3. So on these diagonals over there, which here in this convention is going to be this diagonal here, only 2 elements are repeated, which are the last 2 elements. And then eventually you have the main hyperdiagonal, which goes from here to here, where all the 3 elements are repeated. If you want in 4 dimensions, we can either use colored chalks, or you can imagine that it changes in time, and then you will see also there the main hyperdiagonal will be the hyperdiagonal like this that changes in time, but also all the others will have at least 2 repeated indices. And in any case, any indices that are repeated means you are in any one of the hyperdiagonals, which means the element is 0 because the tensor is hypersymmetric. That's where it comes from.
Is it okay?
Cool.
Thank you.
Sure. So supposing that doesn't happen, we sort the indices because of the top hyperpyramid. We find the raw number with this trick before. I mean, again, you don't have to use this, but I think this is kind of like comfortable to do. So we find the raw identifier, and so we know where to read. But then the question is, was the raw at all stored or not? I suppose we have row number 5, okay? Maybe in these rows here that we are stored, row number 5 is not there. We never stored it, or maybe it is. So the next thing to check is exactly this. Search for the number of the row number R in the list of stored rows. Remember, the metadata, as I was saying, the length, the number of rows that were stored, the identifiers of the rows, and the lengths of the rows. So you search there in the list of the identifiers of the rows that have been stored, whether R is at all there or not. By the way, as we're going to see later when we do writing, these are ordered lists, which means all these searches are fairly efficient because you can do bisection. You just do a binary search, and that complexity is just a logarithm of the number of rows that you are stored. Number of rows that you are stored in sparse data is going to be very, very small anyway, so this is basically, best case, it's all 1, so it's very fast. So anyway, so you search it. If the answer is no, then obviously it means that that row was entirely empty. It was entirely empty, we haven't stored it, so whatever element you're trying to read there is 0. You don't even need to bother, it's 0. You already know, there you go, it's 0. So return 0. That is good. Then the other possibility, of course, is that you find it. So, we have stored the row. And then the question is, if the row has been stored, where is it? So if we say row R, we found it, was it the first one? Was it the second? Was it the third? We don't know. And why we don't know, again, it will be much clearer later when we see how to write. But in principle, what I'm trying to suggest here is that these rows here don't have to be stored necessarily in sequence, okay? Because that depends on how you wrote the tensor. So what if the row is found that it has been stored in the tensor? We need to find where in the actual data it is found. So the way you can do this is you can actually measure the distance within the memory of the computer between the place where your target row starts in the list of the rows and the initial location of memory where the list of rows is actually stored. Then you subtract, divide by the size of whatever type identifier you are using, and you get the result. What I'm saying is this. Suppose that this is the list of rows that we have stored. And say the target row here is the one in red, 25. So this is row number 1. This thing here, this location of memory will be a pointer to this first row in the list of rows here. So that's the memory location of that first row in the list of rows. Here, this location of memory where it says 25, means like you have a pointer to this, which is the target row in the list of rows, which is, again, the memory location of the target row in the list of rows. If you subtract this distance in memory is directly the number, the sequential number of your target row in the matroid of the actual data that you have stored in the computer. Okay? So this way you don't have to go and like search or carry over labels or other things like this. It's also fairly fast because you're operating directly on pointers. You are not even operating on numerical types. You are operating on memory locations, as in like literally on the identifier of memory locations. So this is actually lightning fast, kind of. And this way, you know, say for instance, row 25 is the third sequential row over here. Right now, in this case, it's not. It's 1, 2, 3, 4, 5, 6, 7. It's the 7th actual row that is stored in this example here. So you can go and you can target it directly. So now you know in this thing here where to go and read. At this point, remember, these things here, the elements of each row correspond to the kth element of, to the kth index of the element of the tensor that you're trying to read. So what you can do is you can search within this row whether there is at least one element in the row that is equal to the last index of the element that you're trying to read. Because that will be like the column within that row that you have stored, knowing that that particular piece of data was a 1, so that there was a hyperedge there. If it's there, it's there, it's there. So if it isn't there, if you haven't stored that when you have written the tensor, then it means that the element is 0, and you can just return 0. If you find it, so if you see that it is there, then it means you have stored that column corresponding to the last index of the list of the indices of the element that you're trying to read. It means that that particular edge existed, and therefore the element is a 1. And so you just return a 1. So you may have noticed that in all these, we haven't actually stored zeros and ones. We have stored other stuff, and we are inferring logically the presence or absence of a hyperedge, and therefore returning eventually 0 or 1. The good of this is that you can take this and you can make it transparent. So like you really make a method, read and write, and therefore after that you just forget about it and you can do whatever operations or linear algebra you want by just saying read the element, write the element and all. Then the computer will do transparently this behind the scenes. So it's kind of comfortable to write code. And I think that's the end of the reading, so now we're left with writing. Now writing is a little bit more complex in the sense that it's actually 2 macro steps, so to speak. The first step is what to do, and the second step is how to do it. Now, you can start seeing here that there are colors. Again, we're going to zoom in. This is just the structure of what we're going to see. We're going to zoom in and see what those things are. But you can start seeing that there is a whole logical sequence. This, rather than a flowchart, this is like a decisional tree, to talk about networks, right? And you can notice that there are some ends, 1, 2, 3, 4, 5, 6, 7, and 8. These 3 ends in 8 particular nodes. Of these nodes, 1, 2, 3, 4, and 5 are green, and 3 are red. The green ones, you can't read from there. I can read from here because it's just very, very small. But I know what it says there, and we're going to see it. It says do nothing. So in 5 cases out of 8, you don't have to do anything, even when writing the element, which is what makes it particularly efficient. In 3 cases out of 8, you have to do stuff, of course, because at least once you need to do something. So we're going to see now how to write the elements in this data structure. First thing, it's the same as before, existence check. Remember, like, is the tensor empty? Yes or no? But now there's a twist. It's not just is the tensor empty, is the tensor empty and are we writing a 0? Because I mean, obviously you maybe want to write a 0. So if the tensor is empty and you are writing a 0, then there is nothing to be done because you will still be left with empty stuff. But you may want to ask, like, why do you want to write a 0? It's like if you're only writing ones, like writing edges when they are there, why writing 0? Because, for instance, you're working on adaptive networks and you want to delete an edge. So let's see how many edges I need to delete before the network fragments. So that's when you write a 0. Okay? So you may want to do something like this. By the way, sorry, before going ahead with the writing, I should perhaps stop. Any questions on the reading? We had one before. Any further questions on the reading part? No, okay. Then I continue, fine, very good. So, so if the tensor is empty and we are writing a 0, there is nothing to be done because everything is already 0, so you don't have to write a 0 that is already there. So goodbye, no, nothing done. Alternatively, either the tensor is not empty or we are writing a 1. I mean, the opposite of an AND is the OR of the knots. So if that is the case, then we do the usual pigeonhole count like before. So far, this is kind of like almost exactly the same as the writing. We do the pigeonhole to check for the symmetry. If the element is on a hyperdiagonal, then it's necessarily 0, just the same as before with the cube, the hypercube, the matrix, etc. So far, this is exactly the same. So if that is the case, if some indices are repeated, you are on the hyperdiagonal, don't do anything. Don't do anything because the element is necessarily 0. So regardless of any, you cannot be doing any, cannot be wanting to do anything because that element is 0. So just truncate the whole thing and end up there. So far, so good. Now, suppose instead that the elements are not, so the indices are not repeated, so you are not on one of the hyperdiagonal. Then again, sort the indices because we only want to write elements in the top, uppermost hyperpyramid, and find the row number, again with here, base 10, base n numbers. You find it, we have the row number R. Question, is the row there or not? So search in the rows that we have already stored. Like before, binary search, we will search for it. Two possibilities, either the row is already there, we have already recorded something, or not. If we have not recorded that row, means so far the row is absent, so far for us the row is entirely made of zeros, then ask yourself, are we writing a 0? If so, nothing to be done, don't do anything. Why? The row is not there means that the current state of the tensor is that all the elements in the row are 0. If we are writing a 0, the 0 is already there, so there is nothing to be done. Don't do anything. Alternatively, if the answer is no, so we are writing a 1, because it's either 0 or 1, the row is not there, we are writing a 1, we need to add a row. So we need to do something and put a new row inside here, do something with the lists of rows and all those things. That's one of the 3 possibilities that something needs to be done, adding a row over there. And we're going to see it later. Remember, say 2 steps. First, figure out what needs to be done, if anything, and then figure out how to do it. That's the first part. So yeah, we need to add the row with the correct identifier, etc., as we just said. So there you go. Now we go back. Suppose that the row that we searched instead was already there. This was in the case that the row that we are addressing wasn't there. Now suppose the row that we are addressing is actually there. Well, then we need to find where it is within the actual data. How do we do that? Exactly the same as before. The pointers, the locations on memory, subtract, divide, and you find where it is. So this we know, it's the same method as before. So we find the position in the matroid, and then we search for the last index, because again, the last index here corresponds to the column within that row of the element that we are addressing. And again, there's 2 possibilities. Either you find it already there or you don't. Okay. We are assuming the row we have already stored some of it or even all of it. Suppose that you don't find that element there. If you don't find it, it means that in its current state, that element is a 0. Then you check, are we writing a 0 or a 1? If we are writing a 0, nothing to be done. Why? Again, because the row is there, but that particular element that we want it to be 0 is already a 0. So there is nothing to be done and don't do anything, that's it. Vice versa, if instead we are not writing a 0, we're writing a 1, and we are at this point, it means that we know that that element is not there, so in its current state it's a 0, then we need to add it. We need to add this new element, which is this new column, not that row, the tomographic row that scans the tensor, inside the data there. So this is second case in which something needs to be done. Element is 0, you want to make it a 1. Something needs to be done. First case was the whole row is absent and you need to write it. And finally, of course, we go back up in this decisional tree and we go here. How about instead we already find that element? Let me jump up. There you go. Suppose we already find that element. So that element was already there. It means in the current state of the tensor, that element is a 1. And then we check, are we writing a 1? If so, there is nothing to be done because it's already there. Again, it's already 1, so nothing to be done. Vice versa. If we are deleting an edge, for instance, we are writing a 0 on an element that was 1, then we need to do something. What do we need to do? We need to remove that element, which means remove the column from inside one of these rows, the row number R, that will be sequential row number who knows what. We need to remove the column within there that corresponds to this element that we want to delete. So 3 possibilities in this whole decisional tree, only 3 possibilities that you need to do something. All the others, you don't do anything, which means better because it's fast. So this means now we need to figure out how to do those things. Before I go ahead with the next thing, are there any questions? Like how to write the actual elements on this decisional tree here of what needs to be done if something? Everything clear? I see people saying everything clear, which is cool. All right, very good. So yes, so we need to figure out, this is what I just said now. In 5 cases, nothing needs to be done. 3 cases, we need to do something. So let's see how to do it. Case number 1, we need to add a row. We need to add the row, means we want to write something. The row is not there, means it's the first element of the row that we want to write. And we need to write it, but the row wasn't there. So how do we do this? Well, the first thing is we are adding a row. So remember, there is the counter, the very first element of the data structure. How many rows are we storing? You take that and you may increase it by 1. If we had 5 before, now we have 6. Increase by 1. Then we have the vectors that store the identifiers of the rows, the R numbers, the here base N numbers, this things there, and the one that stores the lengths of each row. You take them and you make them, you lengthen them by 1. Basically allocate an extra piece of memory for each of these 2 vectors. And then you increase the length by 1 of the vector that contains the pointers that point to the locations of memory where these rows actually start, so that you can make a new one. So far, like nothing particular. And here I got a drawing of this stuff over here. So these are the rows that we have stored in this example. Row number 1, 5, 7, these are the R numbers. These are the lengths of the rows, 2, 1, 3, 2, 4, 3, 2, 1, 3, 2, 4, 3. This is a vector of memory pointers that each one of them tells you where the data are actually stored in the computer memory, and these are the actual data over here. So what we do is this. We shift to the right the row identifiers, the lengths of the rows, and the memory pointers that come after the position where we need to put the new row. Okay, so say the new row needs to be added here, so we shift everything to the right. So copy this to the right. Okay. Next, we just write down here the R number. Suppose this was the row with identifier 9 in this example, we put it over there. Then we write its length. Its length is 1. It's necessarily 1 because the row wasn't there before. And now we have added 1 element into it, right? Because the minimum operation, these are atomic operations for the computer scientists here. Are there any computer scientists here? Anyone that studies? You, okay. So this is an atomic operation. So obviously this is 1 in the beginning, and that's it. And then the next thing we need to do is actually add here a little piece of memory for the new row, and we put its pointer at the right position. So, yeah, here I'd like to say something here, because for the one computer science in the room especially, but for everybody. Okay, please note, in this example here, I started with the rows being put all in order. So like first this, and then this, and then this, and then this, and the numbers like this. But now look, row number 9, which will be 1, 2, 3, the 4th row in this example, is at the end of the actual structure of the data. Okay, so these data here are not stored in order. This is what I said before. It will become clearer why we need to do this search when we see how to write. That's how. See, it's not necessarily in order. Number 2, And that's a drawback of this method, okay? Let's be honest here. This does not enforce locality of reference. Question, anyone familiar with the language? Locality of reference. You, yes? You, yes? No. Okay, so locality of reference. Ta-dam. Let's make a small theoretical computer software engineering kind of digression. Suppose you are allocating some piece of memory. Okay, there are two different, I don't even want to call them paradigms, okay, two different ways that people usually can do it. Some people don't care and it doesn't matter. It's you either enforce locality or reference or not. What does it mean? Suppose that your data refer to something like this, a metric, something scientific and whatnot. One possible way of doing it is allocating one huge chunk of memory all together, one next to each other, up to paginations, alignment of pages, which we don't care at in this moment here. The simplest way to do this, for instance, for matrices, just imagine a normal classic matrix. The simplest way to do this, that is also like very fast when you need to write code, is suppose you have an n by n matrix that you want to allocate. You allocate n squared pieces or bytes, n squared doubles, n squared whatever you want. Like this. Okay, etc. Then you make a vector of pointers of size n. And you do. The first pointer here, you make it point at the beginning of your piece of chunk of memory that you have allocated all together. The second one, you make it point n locations away. The third one, you make it point n locations away, etc. This way, when you want to address this, you will address this as element j after the pointer ij. Okay, so this will be like, if we call this m, will be m of 0, 0 will go here, m of 0, 1 will go here, m of 0, n minus 1, m of 1, 0, m of 1, 2, etc. So you can literally, transparently address a matrix, whereas in reality you're addressing a whole chunk of memory with the memory altogether. Advantages of this, you take this, you cache it in the CPU, and you do whatever operations you want super fast. You don't have to transfer data to and from memory continuously. Disadvantages of this. Suppose you have a bug. You have a pointer underflow, pointer overflow, or something like this. You will be overwriting data. So as soon as you have the smallest possible minimum bug, this is going to screw up your results guaranteed. Okay? So this is the traditional way of using memory for scientific applications because it's very fast. And this concept of putting next to each other, next to each other in the computer memory, the data that are close to each other in a semantic sense is called locality of reference. This method does not enforce locality of reference, unfortunately, because it means it's a bit slow. But then again, as Stefano says, a trade-off, we need to figure out what to do. Incidentally, there are some programming languages that by themselves, by default, do the opposite. So by default, they actually try not to enforce locality of reference. The most infamous example of it is obviously Python, which is the reason why, one of the many reasons why Python is not a scientific programming language. And it does, like sparse is better than dense is one of the mantras of Python. So do not use Python for scientific programming, except if you have a few centuries to wait, basically, for your simulations to finish. In that case, it's fine. So that was the drawback. Non-locality of reference is obviously great when you're doing programs that have like a lot of user interaction. If you're building a GUI, the time that a user moves the mouse and clicks or something, obviously, you don't need lightning fast reactions in the meantime from the computer. So, and incidentally, if you have a bug there, chances are that these chunks of data here are padded by rubbish around. So if you have typical pointer bugs and you are very lucky, you should still correct them, you may not end up having bad results at the end. So after this long digression, we go back to how to write here. So this, we have added the element, and that's it. Yes, by the way, this has not moved the data. The data that were there have remained static, which means that this whole operation is actually also quite fast. Now, number two possibility is how to add a column if the row already exists. So this is kind of like the same as we saw now, but even simpler. So suppose, click, click, I'll just go like this, there you go. Suppose that you know in which row we are adding an element, like in the red one over here. Okay, so this row here, row number 12, which is actually 1, 2, 3, 4, 5, the sixth row, 1, 2, 3, 4, 5, no, the fifth or whatever it is here, okay? So what we need to do here is simply we go here and we increase the length of the row by 1 in the list of lengths of the rows, and then we find where the row is in the matroid. So the pointer is this one, and this over here, and we add an element at the end. So we allocate an extra little piece of memory. Then we shift to the right the elements that are already there at or after the index where we need to insert ours. This is kind of like insertion sort, again, for the computer scientists. And we put the element in the right place. That's it. So this is kind of, yeah, this is all like a multidimensional insertion sort, if you want to look at it from this point of view. And as well, that was very easy, it's simpler than the previous one. Last is how to remove a column. So remove a column, again, we find which column we want to remove. Say this element here in this row, the one with the letters, the red one is the one that we want to remove. So we know which one it is. All that we do is shift the elements to the right of it one step to the left. So the D that was here has overwritten the C. Then we need to obviously decrease the, I'll just really click with my hands, it's easier, there you go. Decrease the length of the row. Before it had 4 elements, now it's got 3 elements. And that's it. However, you need to be careful. Suppose you are removing the last element of a row. So suppose instead of removing this element C, we're removing this element X here of row number 5, which is the second, is it the second? Yeah, the second row that is stored over there. If we remove this, that row will become empty. So the row will disappear. We need to take care of that. How do we know when that is going to happen? We know it because the current length of the row is 1. So if you are removing an element from a row whose current length is 1, then you know that you are going to take the row and make it empty. So what you do is don't remove the data because there is nothing to copy over, as we said before. So the length is now 0, but nothing remains over here. So this that used to be a pointer to here, now it's a dereferenced pointer that is invalid, so you need to be careful there. How do we address the situation? The row is no longer there, we just get rid of it. That's simple, just remove the entire row. So we knew that this row was here, we shift every element here from right to the left, overriding everything. We shift all these elements here from the right to the left, overriding everything. And the same thing over here, all the pointers, we override, shifting them one position from the right to the left. And we don't even care about the previous pointer. Why so? Because in the moment that before we have removed the element, we have deallocated that memory there. So the memory is already free. This guarantees that you have no memory leaks. In some cases, if you do that without doing this, slowly, what's the? Yes, it's Albert here?
No, before, don't worry. Until you finish the first part, then we have the coffee break, and when we resume, Albert will start saying something.
Perfect. Okay, so this way you avoid memory leaks. And yeah, that's what I just said, in fact, here. And finally, if this happens incidentally, you may even the higher order case where you have removed all the rows one by one, and that was the last row. In that case, you don't need to do anything special. Why so? Because this whole procedure would have made it already, will have brought you at a situation that all the pointers that need to be removed and freed have been removed, all the indicators there have been eliminated. So if this has actually made the whole tensor empty, you're actually fine, because you already even know it in the counter of the rows that you have stored that is 0. So there is nothing extra that needs to be done. And what's the time right now precisely? I don't know. I don't have a... Sorry? Okay. No, because if no problem. No, because if it was like right now was a perfect moment to stop. This is why I said I thought it was precisely whatever 11. No, perfect. No problem. Okay, so this is how you can make a data structure, an efficient data structure, to store higher order networks. The way that. So again, just summarizing what we have done is we've shown how to store all the different adjacency tensors from size 2 to size whatever the rank of your higher order network it is, and you put them there, and you can use them. So we're going to see now application of this data structure. I said several times that this is transparent to do operations such as matrix multiplications, tensor algebra, and so on and so forth. So this is what's going to be next. So before starting with this, which the typical thing is community detection, any questions on the whole previous part? Yeah, all clear? Yeah, okay. No, maybe, no, cool. All right, so community detection means finding communities, meaning finding sets of nodes that are typically more densely or strongly connected within themselves than between themselves. Now, there are typically many methods that have been used for traditional networks. The most powerful ones use spectral methods like eigenvalues, eigenvectors, and so on. That's why I said this is a typical example of a method that can use these data structures. And what we're going to do now is we're going to see exactly one such method on higher order networks, like in detail how to build an algorithm that does that. And again, because of all the considerations that we've done before, we're going to consider every order of interaction by every order of interaction. So we fix k. If you have many orders, you repeat it for every different value of k, which means technically we're dealing with k uniform hypergraphs. So one method that has been very successful in traditional networks is that of modularity. Now, what is modularity? At the end, it is a score function. It is an objective function. You take a network, you make a partition, and you make it. Means like you decide, I want to put you there, you there, you there, and you make your partition. Then you take this partition, you pass it to the function, and the function gives you a score. And the higher the score, the better. So typically, modularity algorithms, what they are trying to do is to find a partition that increases, maximizes the modularity. So this is the idea. Again, modularity is like a tool. Something gives you a score. How good is this painting? How good is this coffee? How good is that partition? That's it. And you want to make it as big as possible. What is it based on? It's based on, suppose that you take this partition and you see how many edges you have within the communities and how many edges you have between the communities, and you consider that. Now, you take it and you randomize everything by keeping the degree sequence. So now you take all the edges away, we put them randomly, but we keep the degree sequence. Right? How would this distribution change? How will this difference between the edges that you have observed within and between the communities change? If it wouldn't change much, then it means that your partition wasn't that great, so the modularity score is kind of low. If it will change a lot, it means your partition has really taken all the things and separated them neatly, and then it means that the modularity score will be high. So that's the traditional idea. Suppose we want to extend it to the case of k-uniform hypergraphs. You can write it down, you can do some churning of formula, and you end up with this. So this is the hypermodularity, as I call it, of a partition. So again, what we have there, M is the number of edges that you have. This down here is a sum over all the possible sets of k nodes, of k vertices, including repetitions. So here, we're not going to do the diagonals, they are included. We're summing over all the possible combinations, including repetitions. This is the adjacency tensor of size k. These are combinatorial factors that will become important, if you want, for various other considerations if we have time. dv whatever I is the degree of node I. These are Kronecker deltas, which means 0 if the arguments are different, 1 if the arguments are the same. And CVJ, CVI are the communities to which we have assigned node I and node J. Again, communities to which we have assigned, again, because this is an objective function, you decide how you want to split the network, and then you plug it in there and you get a score. Okay, so it's your decision. Of course, now what we're going to find or try to find is how to make this decision the best. Now, in traditional modularity, when you write the modularity equation, and this was great work, 2006, Mark Newman was on PNAS, you can write it down and you can very easily see immediately that that is a matrix equation. As a matrix equation, boom, eigenvalues, eigenvectors, linear algebra, we know everything about it. But in this case, this isn't exactly a matrix equation. It isn't at all. It's not at all a matrix equation. Which means that all these ideas that have worked so well, we cannot really apply them. Certainly not directly. However, we have ways to go around it. So the first thing that you can notice is, again, assuming that you have a simple hypergraph, those without repetitions of edges, without repetitions of nodes within the edges and all, then this thing here, this A, this adjacency tensor, you can imagine, you can think of it as a stochastic variable, specifically something called an indicator variable, which are Bernoulli distributed stochastic variable, and I'm calling like with a bold 1 over there. This basically kind of like tells you whether something is there or not. So this means that the whole here, this whole term here in the round brackets, this A minus combinatorial factor times product, you can interpret it as if it were a hypersymmetric data tensor. We call it B here. Hypersymmetric data tensor B that equals this. Okay. But then if I take this, I can just plug it in the modularity equation, and I find that this is my hypermodularity equation, reinterpreted it in a language of data science, if you wish. Yes? Yep. Yes, yes. And that's why we need it to be simple. Exactly, precisely. So now we have this here. So now why does this, how does this lead us anywhere? Well, as I said, this is typical language of data science. So what do people do when they want to do a classification task on multidimensional data? Because at the end, saying you belong to community 1, you belong to community 1, 2, you belong to community 2, community 1 again, community 3, whatever, that's a classification task. So typically, when people want to do this, nowadays, they say, hey, we can do higher order SVD, higher order singular value decomposition. It works amazingly well, machine learning, all these things here. I say, okay, can we do it here? So why not? Let's try to see how it works. So first of all, what is an higher order SVD? I think it's fairly common nowadays, but just to make sure everyone on the same page, it's a compact singular value decomposition that you operate on one of the standard flattenings of the data tensor. Now, what is a standard flattening? Standard flattening is kind of like a dimensionality reduction operation. You take this higher order object, you take all the dimensions except one, your choice, and you flatten it onto one direction. And then the one that you have kept remains there. So this ends up giving you a weirdly shaped two-dimensional object. So the formula is basically this. Note E of I here. I is the direction that we leave, the ith direction, and all the others, we compact them onto one other direction. This should hopefully start showing you what problem we're going to have to solve first, basically, before continuing. But why do we want to do this? And then we go back to the problem, is this. When you do the compact SVD, normally you end up with this result, that your matrix X gets cast as a product, like U sigma V dagger Hermitian conjugate over there. Sigma is a diagonal matrix containing the singular values, by the way. But in our case, all the flattenings are real, which means that here what we're actually getting is U sigma V transpose, where U is a real orthogonal matrix. But a real orthogonal matrix of dimension n spans Rn, the space Rn. In turn, this means that if we go back over here, you see there is this product, sorry, not this product here, this product of deltas in this equation next to B. If we find a way to cast this product of Kronecker deltas in a way that separates the variables, then we can try to use the results of the SVD here we can exploit them, by taking the vector, the left singular vector corresponding to the biggest singular value, and saying that that is the assignment that corresponds to the classification, the assignment that maximizes the hypermodularity. This is the same as taking a matrix and saying, okay, I can diagonalize it, and not only that, I can diagonalize it with an orthonormal basis of eigenvectors. Well, but then, if I take the eigenvector corresponding to the biggest eigenvalue, and I multiply it by that matrix, I get the biggest gain. That's exactly the same. So how do we do that? Like, let's see, can we do that? Yes. How do we do that? We do it in a certain way, which we're going to see, but now we go back here to the problem. E of I, right? So if you have a K uniform hypergraph, you have K possible flattenings. Which one is the right one to use? Oops, sorry, the first question, right? There's two things to see. One is which of the K possible flattenings to use. And the answer is it doesn't matter. And I'll show you why. This is the Kth flattening, so the last one, like from 1 to K. If you write it down, it will look like this. The first element is B1, B211, BNN1, etc. Now notice, the ij element in the flattening, so ith row, jth column, in the first row, all the numbers change except the last one, except the kth one, which is 1. The second row, all the numbers change except the kth one, the last one, which is 2, etc., all the way to n. So the ij element of this flattening is the element of the data tensor whose last index is I. Here. The last index is 1, last index is 2, last index is n, and it's the same here. But the other indices have something exactly similar to this. Remember the base n, base 10, it's exactly the same. The other indices satisfy this equation here. This is like rewriting this number here, like the first k minus 1 indices, go here, go inside here, rewriting the number of the k minus 1 indices in base 10, whereas here here they are the digits of a number in base n. Exactly the same as we were doing before for the data structure. So this is for the kth flattening. Now let's write the xth flattening, like a generic one. Take a number x from 1 to k. Okay, we see. So let's do another one. This is how it looks like. Now look, here it is no longer the last element. The last element changes. Now it's the xth element here that in each row remains the same and that changes with the rows. 1, 2, 3, n, 1, 2, 3, n, etc., etc. So again, in the xth flattening, the element ij is the element of the data tensor where now its xth index equals I, and the other indices, index number 1, index number 2, index number x minus 1, x plus 1, and all the way to k, obey the same equation. X remains static there, it doesn't matter, and this is the column number j that we are looking at. Okay, However, this j here and this j here, if they are the same, like if I'm fixing j, I want j equals 10, for example, or j equals 15, then these digits here have to be the same. If I write the number here, 1234, in base 10, and I write again the number 1234 in base 10, its digits will always be 1, 2, 3, 4. So here, the solution to this equation here, in this case, will still be a 1, 2, 3, 4, and here will be again 1, 2, 3, 4, even though maybe their positions have an x in between here, whereas before had a k at the end. Okay? That's because representation of integers is unique in a given base, and that's classic results in discrete maths. So let's now take a completely generic element Lm of the kth and of the x flattening. In the kth flattening, we write it like this. In the x flattening, we write it like that. But now look, V1 is here and V1 is here. V2 is here and V2 is here. X minus 1 is here and x minus 1 is here. Now Vx now will correspond to this Vx plus 1 for the reason that I just said, because the digits are the same. Even though we have put it here an L in between, the digit is still the same. It's just in a different position. This will be shifted there, this will be shifted there, this will be shifted there, and L from the last position will be shifted in the middle. So we are literally taking an L from the last position, put it in the middle, and we have left all the other numbers the same. Why? Again, because they are the digits in a power expansion of the same quantity, and so the solution is unique. But this means that these indices here and these indices here are literally the same up to a permutation. But our tensor is hypersymmetric. And this means that these two elements are the same. If I choose an L and an M, if I choose a row in the column of the flattening, regardless of which flattening I take, the elements will still be all the same, which means take whatever you want. Doesn't matter, they're all the same. So I'm taking the kth one, the last one, just to fix the ideas, but you take the first, the second, you can take them all. So what's the time? Because this is another good moment to stop. In fact, I should stop anyway, I believe. Well, okay, what's the time, guys?
It's 47.
47?
10 minutes for questions.
Perfect. Perfect. This is perfect moment to stop here. Okay, so questions up to now. Questions for the future will be even more interesting if you have questions from what is about to come, because violation of causality is always nice.
Thanks for your presentation till now. I saw that this spectral analysis you did is very close, very similar to singular spectral analysis. The SSA, was this an inspiration for this methodology?
Not really, not really. And the reason is gonna come kind of like that's the next thing in the next hour. I can anticipate that basically the thing was more like I think it was more like, why was it so successful up to now? And what I'm going to show you as a side effect, as a byproduct of the whole demonstration we're going to start with in the second hour, is that actually this specific approach gives you exact, not approximate results in classification tasks. So as a byproduct, we are going to explain why a particular type of machine learning is actually explainable and how to explain it. That's a byproduct. I don't care about that. I care about networks. So not exactly.
Okay, thanks.
Okay.
Thank you.
Sure.
I have a question about when you define J.
Uh-huh.
How can you define that? I didn't understand it.
J, you mean
The index.
like this here?
Yeah, yeah.
Okay. So, there it is. So, J is the column. First column, second column, third column, nth column. Okay. The last element here is our I, because you see in the first row the last element is 1, in the second row the last element is 2. So we forget about the last index. We take only the first k minus 1 indices here. So now look, it's exactly here. It's like 1, 1, 1, 1, 1 is 1. Yeah. 2, 1, 1, 1, 1. So just here the increment is from left to right, not from right to left. 2, 1, 1, 1, 1 is 2. N, 1, 1, 1, 1 is n. Then 1, 2, 1, 1, 1, 1 is n plus 1. It's not written here. Okay. So if you count them, you go like 1, 2, 3, 4, 5. Have you ever seen a counter like an analog counter? Have you ever seen the cassette recorders? Often they had these little numbers that were turning. Have you ever seen that? No. I'm old. I'm so old. Okay. So it's something like this. Sorry, what? We. Okay, so it's kind of like something like this. This is actually how I thought about it. And this is literally something like this. And you're turning and turning, and then when it turns, the next number overturns. And you go again, everything is 0, and the next one now is bigger, 1, 2, whatever. So how do you write that number? If you think about it, that is, again, the power expansion of the sequential number in a given power. Now, if it is in base 10, like how 1, 2, 3, 4 that I was saying before, that is literally, this means that it's turned 4 times, then it's turned 3 times, 10 times, it's turned 2 times, 100 times, and 1 time, 1,000 times. And that's exactly how it is here. Now you get some minus 1s here because the digits, except for the first digit when we write numbers, except for the first, the others can be 0. That's why the first one is 1 and the others minus 1, minus 1, minus 1. But it doesn't matter. It's still a power expansion. And instead of being in base 10, here we go to the next number that changes after we have gone through n of them, from 1 to n, and then and switches to the next, which means that the powers here, the base, rather than being 10, is n. But then, literally, this is this equation of integer representation. And again, from like discrete mathematics 1, we know integer representation is unique, which means that if it works here, these digits, which are v1, v2, v3, the solution to this equation, will be the same also here, etc., etc., etc. Thank you.
Other questions? No? Okay, if there are no other questions, we thank the speaker, and we go for coffee break, and we return 11:30.